Hi and welcome to Maths class. Today we're going to look at a technique called integration by recognition. And the name in the title is really important because we use a kind of trick when we do it, which is when we recognize that the integral that we're looking for, well, the function that we want to integrate is the derivative of another function that we know or looks very similar to another function that we know. So we don't so much antidifferentiate as recognize that this is the derivative of another function. I'll show you how it works. It'll make more sense. The example we're going to use first is a fairly straightforward one, and here's the example. Now, I definitely don't need this technique to differentiate this particular example. I'll just move that a little bit so you can see it. Hang on. That's better. All right. So we're going to differentiate the function y equals 5x plus 1 cubed. And then in part B, we're going to use that result to find an antiderivative of what we can see there, 3 times 5x plus 1 squared. So let's just do the first part. We need to differentiate this function here. So to differentiate, okay. There it is. So I've differentiated by, first I need to multiply by the power 3, and then because this is a chain rule, I need to multiply by the derivative of the inside function, which is 5, and I get 5x plus 1 squared. So my grand total is going to be 15 times 5x plus 1 squared. 15 squared. Okay. So, but I'm asked to use this result to find the antiderivative of 3 times 5x plus 1 squared. So what I'm really interested in here is the link between the 3 times 5x plus 1 squared and the 15 times 5x plus 1 squared. There's just a factor of 5 between them. So this is what I found with my result A. I found that the antiderivative of 15 times 5x plus 1 squared dx is going to be equal to the function I started with, which is 5x plus 1 cubed. I can put in a plus c, but it does say find an antiderivative, so I don't need to, but let's keep our plus c's. But that's not what I'm looking for. This is a 15 here in the front. I want it to be a 5. So I'm going to just rewrite the left-hand side by taking out a factor of 5 and leaving the factor of 3 inside the derivative, the antiderivative, and then the rest of it will stay the same. And it still equals the same on the right-hand side. Okay, now what I can do is simply divide both sides of my equation by 5. Divide that by 5, divide that by 5, the whole thing. And that's going to leave me on the left with 3 5x plus 1 squared dx equals, on the right hand side, it's going to be 1/5 times 5x plus 1 cubed. Now, I'm just going to throw in a plus c, even though this c is different from the c I started with. It really doesn't matter because c is any constant number, any real number. So it doesn't matter whether it's divided by 5, it's still any real number. So this is how I do this, right? What I didn't do was I didn't look at 3 times 5x plus 1 squared and think, how do I anti-differentiate that? I was given a hint in the question. First, I was asked to differentiate this function, and then I see that the result that I get resembles the function that I want to anti-differentiate. So if I differentiate this, I almost get something that looks like this, but it's just slightly different. So then what I do is I simply manipulate what I've got in order to get the answer I'm looking for. I'm going to show you another example. Differentiation by integration by recognition is really a technique that is best understood by looking at lots of examples. So let's go to our second example. Okay, there's my second example. I need to find the derivative of e to the power of x squared. So before we even go to the next part, let's think about that. I need to define the derivative. This is a chain function. It's a composite function, which means I'm going to use the chain rule, all right? And then I need to use my result to find the antiderivative of 6x times e to the x squared. Now, let's look at the function I'm going to antidifferentiate. At the moment, I do not know how to antidifferentiate that. I wouldn't even know how to antidifferentiate e to the power of x squared, let alone 6x times e to the power of x squared. I haven't learned any rules or formulas that help me to do it. However, because of the way the question is written, I feel confident that after I have found the derivative of this first expression, it's going to give me a clue as to the antiderivative of the second expression. Now let's be careful with our notation. The first expression is not given to me as a function, it's just given to me as an expression, e to the x squared. So I'm just going to write d dx of e to the x squared, squared equals. And this is a chain rule. Now I'm going to do this the short way, but I'll talk you through it. This is the same as e to the power of another function. So what I'm going to end up with is the derivative of e to the power of something multiplied by the derivative of the function inside. So the function inside x squared has a derivative of 2x. And then I have to, if I remember, this is like e to the u, and the derivative of e to the u is just e to the u, but u is x squared. So let's write it properly, 2x e to the x squared. Okay, so what I've found is that if I differentiate e to the power of x squared, I get 2x times e to the power of x squared. That means that if I antidifferentiate 2x times e to the power of x squared dx, I'm going to get what I started with, e to the power of x squared, and throw in a plus c. So I now know what the antiderivative of 2x e to the x squared is. I'm actually really close to finding out the antiderivative of 6x times e to the x squared. So all I need to do is multiply both sides of this equation by 3. If I multiply the left side by 3, I'm going to end up with a 6 here instead of a 2. So that's 6x e to the x squared dx. And on the right hand side, if I multiply by 3, I'll just get a 3 here times e to the x squared plus c. So integration by recognition relies on me first differentiating something and then recognizing that the derivative function that I get is very similar to the function that I want to anti-differentiate. And because these are reverse processes, then I can go from here down to here, and that will help me go backwards from the function I want to anti-differentiate. Let's look at another example. All right, in this example, I'm asked to differentiate log of 5x squared minus 2, and hence to anti-differentiate x over 5x squared minus 2. And I don't have a rule for anti-differentiating this function, x over 5x squared minus 2. This is not something I can easily anti-differentiate, but also I need to obey the question. It wants me to do it by first differentiating this logarithmic function. So this is another chain rule. Let's do this one the long way because actually no, I don't need to, because I know the rule that, whoops, I need a pen, hang on. I know the rule that the derivative of any log function that is a chain rule with a function inside, the derivative of that is going to be the derivative of the function inside over the original function. This is a rule that we learnt when we were doing differentiation. So I'm going to use that here to find the derivative of the function log base e, and that should have an e up there, log base e of 5x squared minus 2 is going to be the derivative of the inside function, which will be 2 times 5x, so that's 10x, minus 2, well, the derivative of negative 2 is 0, so just 10x over the original inside function, which is 5x squared minus 2. Now, let's look at the function that we're asked to antidifferentiate, and you'll see that now this looks much more familiar. And one of the reasons this is called integration by recognition is that you learn to recognize when the function you've got is a standard differentiation. If I've learnt that log base e of f of x is the derivative of the inside function divided by the inside function itself, then I can see that although this function I've got here doesn't exactly match because there's no 10 on the top, the only thing I'm missing is multiplying by a number 10. I'm not missing any x's or anything like that. So that makes it really easy for me to edit and change it to what I want. So the first thing I'll start doing is writing down what I've found by differentiating. If the derivative of log base e of 5x squared minus 2 is equal to this function down here, 10x over 5x squared minus 2, then that must mean that the antiderivative of that 10x over 5x squared minus 2 dx is going to be what I started with, log base e of 5x squared minus 2. Okay, plus c. Gonna run out of room. Don't forget your plus c's. All right, but I don't want the 10. So I'll take it out the front on the left-hand side, and now I'm left on the inside with x over 5x squared minus 2 dx, which equals the same still, log base e 5x squared minus 2 plus c. So all that's left to do now is divide both sides of my equation by 10, and I'm going to have then the antiderivative of what I'm looking for. So the antiderivative of x over 5x squared minus 2 dx is the right-hand side divided by 10. So 1 over 10 times log base e 5x squared minus 2 plus c. Again, you don't need to worry about manipulating your plus c's, making it divided by 10, etc. Okay, because that plus c means my c can be anything. So it doesn't matter if I divide it by 10. Okay, so to reiterate, what we do here is we don't go to the function that needs to be anti-differentiated and look at that and go, oh, what is the rule for anti-differentiating that? I just don't know. We don't look at that. We start by differentiating something else, and then what we look at is the connection between the answer we got and the thing we want to anti-differentiate, and I can see all I need to do is divide by 10. That means that the thing I started with is just 10 times the antiderivative of this thing over here. Right, I have one more worked example to show you. So let's go there. This one's a little bit trickier and ever so slightly different, but let's have a look at it. I need to differentiate x cos x and hence find an antiderivative of x sine x. Now the first thing that's different is I don't have a chain rule here. This one of course is a product rule because I've got a function x multiplied by the cos x. So let's start by differentiating this. Actually, what I'll do is I'm going to do this the long way, just to make sure everyone knows what I'm doing. So first, let's let y equal this function x cos x. Then I'm looking for dy dx, but I'm also going to let u equal x and let v equal cos x. That means du dx is equal to 1 and dv dx is equal to, well, the derivative of cos x is negative sine x. Now what I need to do is use my product rule, which means that I basically multiply du dx times v and dv dx times u and add them together. So dy dx is going to be this du dx times cos x, 1 times cos x, and then I add this x times this negative sine x, which gives me negative x sine x. All right, now before I even look at the thing I want to anti-differentiate, let's write down what we've found. If the derivative of x cos x is equal to cos x plus negative x sine x, then I know that the antiderivative of cos x plus negative, let's just write minus x sine x dx is going to be equal to x cos x. Now, what's tricky here is how do I change this antiderivative cos x minus x sine x to match the thing that I need to anti-differentiate. Now let's remember, I'm not going to do this by trying to anti-differentiate x sine x. I'm going to take what I know and rearrange it until I have an expression that looks like this. I've got that on my left-hand side, and on the right-hand side, the answer, right? If I rearrange this equation, then I will know the answer, even though I haven't actually anti-differentiated this. So the first thing I'm going to do is split these up. This is going to be cos x dx minus the antiderivative of x sine x dx, still equal to x, cos x. And now what I can do is I can take the cos x, the antiderivative of cos x dx that I've got on the left, and I can just subtract it from both sides of my equation. So I'm left with, on the left side, negative x sine x dx, and on the right side I've got my x cos x still, and I've subtracted the antiderivative of cos x dx. I'm going to run out of room here. Get rid of that. All right. So what I'm dealing with here is an equation, right? This equation here, I know is true because I differentiated the right-hand side, and I got this expression on the left. Therefore, if I anti-differentiate this on the left, I'm going to get this on the right. I know this is true. So far, I started with an expression that's true. And now all I'm doing is adding and subtracting and doing things to rearrange the equation. And as long as I do the same to both sides of the equation, then still true, right? This equation is still true. So what I'm going to do now is I'm going to do two steps at once, only because I'm running out of room here, is I don't want this negative sign on the left. I want the antiderivative of x sine x. That's this part in here. So I'm going to multiply both sides of my equation by -1. Actually, I won't do two steps at once. Let's just do that. Multiply both sides of my equation by -1. On the left, I've now got x sine x dx. And on the right, I've got negative x cos x. Oops. Plus the antiderivative of cos x dx. I'm nearly there. This is what I'm looking for on the left-hand side. I don't need to touch the left-hand side anymore. I just need to find out what the right-hand side actually equals. So negative x cos x, I'm fine with that, but I've still got an integral sign on the right-hand side. Well, that's okay, because the integral I need is one that I can actually do. I can do the antiderivative of cos x, and I know that the antiderivative of cos x is sine x. So this is still true because these two parts are equal. The antiderivative of cos x dx equals sine x. Okay, don't forget your plus c's. All right, I've been forgetting them all the way along. I'm just going to throw it there in there at the end. Well, let's put one on this line too. Plus c, plus c, plus c, plus c. And we're done. So that last one was pretty tricky, and so I did go through it slowly. But the thing that gets confusing about this is people want to find a rule to anti-differentiate something, and that's actually not what we're doing. What we do is we first differentiate something, and then we recognize that as very close to the thing we want to anti-differentiate, and so we use the connection between them. All right, that's the end of the video on integration by recognition.